Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a fascinating paper, Energy. Base transformers are scalable learners and thinkers. It's a bold claim, so let's unpack it, shall we?
Definitely a provocative title. Thinkers is a strong word. I think what's really interesting here is the potential for these energy-based models to move beyond just pattern recognition, which has been the hallmark of deep learning so far.
I'm immediately skeptical, I have to admit. The hype around deep learning has been deafening, and I'm not convinced simply tweaking the architecture is going to magically produce thinking machines. We've seen this before, haven't we? Neural net winters and summers, and what really changes.
Okay, fair enough. So let's break down what an energy-based model is in the context of transformers. Traditionally, transformers rely on attention mechanisms to weigh the importance of different parts of the input sequence. Energy-based models, on the other hand, define an energy function that assigns a scalar value to each possible state of the system. The lower the energy, the more compatible that state is with the data.
Right, and that energy function is key. It's essentially a learned representation of the underlying structure of the data. Think of it like a landscape. The valleys represent stable, low-energy states that correspond to meaningful patterns, and the hills are unstable, high-energy states that are less likely to occur. The model learns to shape this landscape based on the data it sees.
Okay, I get the basic idea. But how does this translate into thinking? Are we just saying it's a better way to find correlations in data? Because that's not thinking, that's just statistics on steroids.
Yeah, that's the big question. My concern is that it's still just curve fitting, albeit in a more sophisticated way. To me, true intelligence requires the ability to reason, to generalize beyond the training data, and, crucially, to understand the underlying causal relationships. Can these energy-based models do that?
Well, the paper argues that by learning an energy function, the model is implicitly learning a deeper understanding of the relationships between data points. It's not just memorizing patterns, but rather learning the underlying principles that generate those patterns. They seem to suggest it helps with abstraction.
Exactly. Think about it this way. A standard transformer might learn that cat and dog are both related to animal because they frequently appear in similar contexts. An energy-based transformer, if properly trained, might learn a more abstract representation of animal nesses based on shared features and relationships, regardless of the specific labels cat or dog. This is crucial for generalization.
I'm still not convinced. That sounds like wishful thinking. How do we know it's not just learning a more complex statistical mapping? How do we test for genuine understanding? We need benchmarks that go beyond simple classification tasks.
Agreed. We need tests that probe the model's ability to reason about counterfactuals, to perform analogies, to understand causality. Something beyond just predicting the next word in a sentence or labeling an image.
Right, and that's where the scalable part of the title comes in. The authors argue that energy-based models can be scaled to handle more complex tasks and data sets without the same performance degradation that plagues traditional deep learning models. They point to the fact that energy-based models offer a more structured representation, which may lead to better generalization.
And that scalability is tied to the efficiency of the energy landscape itself. If the landscape is too complex, with too many local minima, the model will get stuck and fail to learn effectively. So, the challenge is to design energy functions that are both expressive enough to capture the complexity of the data and smooth enough to allow for efficient optimization.
Okay, but let's talk practical applications. Where could this technology actually make a difference? Beyond just beating humans at Go, which frankly doesn't impress me much anymore.
I see a huge potential in robotics, particularly in tasks that require real-time adaptation and planning. Imagine a robot navigating a complex environment, not just by following pre-programmed instructions, but by constantly adjusting its actions based on the perceived energy landscape. It's understanding the relationship between the space it's in and its potential actions.
Yes, and consider personalized medicine. Energy-based models could be used to analyze complex patient data and identify subtle patterns that are indicative of disease. The energy function could represent the patient's overall health state, with low energy states corresponding to healthy conditions and high energy states corresponding to disease.
Absolutely. And think about materials discovery. We could use energy-based models to predict the properties of new materials based on their atomic structure. The energy function would represent the stability of the material, with low energy states corresponding to stable, potentially useful materials.
Okay, those are interesting possibilities. But I still think we need to be cautious about overstating the capabilities of these models. We're still a long way from building machines that truly understand the world in the same way that humans do. And I keep coming back to the limitations of purely statistical approaches.
Exactly. The key, I believe, lies in incorporating spatiotemporal reasoning into these models. Current AI struggles with understanding how things change over time and how different locations relate to each other. We need algorithms that can translate between different coordinate systems, both literal and abstract, to truly understand the world.
Donald, that's a fascinating point. How would you envision incorporating spatiotemporal reasoning into an energy-based transformer?
Well, the energy function itself could be made explicitly dependent on both spatial and temporal coordinates. For example, in a robotics application, the energy function could represent the robot's belief about the safety and feasibility of different actions in different locations at different times. The robot would then choose the action that minimizes its overall energy, taking into account both the immediate consequences and the long-term effects.
That's a really interesting idea. It's almost like building a predictive world model into the energy function itself. But how do you deal with the complexity of real-world environments? The energy landscape could become incredibly high-dimensional and difficult to navigate.
And that's where I think we need to consider neuro-symbolic approaches. Instead of relying solely on energy functions to capture all the complexity of the world, we could combine them with symbolic representations and reasoning algorithms. This would allow the model to leverage both the statistical power of energy-based models and the logical reasoning capabilities of symbolic AI.
Sarah, could you elaborate on that? What would a neuro-symbolic energy-based transformer look like in practice?
Sure. Imagine a system that uses an energy-based transformer to process sensory data, such as images and sounds. The transformer would learn to extract relevant features and represent them as low-dimensional vectors. These vectors would then be fed into a symbolic reasoning engine, which would use them to build and manipulate symbolic representations of the world. For example, the system might learn to represent objects, relationships, and actions using symbolic predicates and rules.
So, it's like a hybrid approach, combining the best of both worlds. The energy-based model handles the messy, unstructured data, while the symbolic engine handles the high-level reasoning.
And how would these two components interact? Would they be trained separately, or would there be some kind of joint training process?
That's the million-dollar question. There are several possible approaches. One is to train the energy-based model to produce representations that are easily interpretable by the symbolic engine. Another is to use reinforcement learning to train both components jointly, with the goal of maximizing some overall reward function.
This is really compelling. So let's circle back to the original claim. Energy-based transformers are scalable learners and thinkers. Based on our discussion, would you agree with that statement?
I'm more optimistic than I was at the beginning. I think energy-based transformers offer a promising path towards more intelligent machines, particularly if they can be scaled effectively and combined with other techniques, such as symbolic reasoning.
I'm still skeptical about the thinker part. I think we need to be very careful about anthropomorphizing these models. But I do agree that energy-based models are a valuable tool for learning complex relationships in data, and I'm excited to see how they can be integrated with neuro-symbolic approaches.
I'm cautiously optimistic. I see the potential, but I think we need to focus on incorporating spatiotemporal reasoning into these models to truly unlock their potential. Without that, I fear we'll just end up with more sophisticated pattern matching engines.
Okay, so let's shift gears and talk about future research directions. From your perspective, what are the most promising avenues to explore in this area?
I think we need to focus on developing more efficient and scalable energy functions. The complexity of the energy landscape is a major bottleneck, so we need to find ways to reduce its dimensionality and make it easier to navigate. Also, a deeper understanding of how the energy function compares to traditional cost functions is important.
I think we need to focus on developing better neuro-symbolic algorithms. We need to find ways to seamlessly integrate energy-based models with symbolic reasoning engines so that we can leverage the strengths of both approaches. How do we automatically translate the knowledge learned in neural networks into a symbolic representation? I think there is value in that.
I think we need to focus on incorporating spatiotemporal reasoning into these models. We need to develop algorithms that can explicitly represent and reason about space and time, and that can translate between different coordinate systems. We have to be able to move between coordinate systems to see if we can build a framework for the translation between ideas and representations.
From my perspective, I'm particularly interested in exploring the connection between energy-based models and the brain. Can we use insights from neuroscience to design more biologically plausible energy functions? How can we bridge the gap between the abstract mathematical representations used in these models and the actual physical processes occurring in the brain? We need to understand how various areas of the brain interact. I'm also interested in brain-computer interfaces. If we can better understand how the brain processes information, it could inform the design of AI architectures capable of learning and adaptation in a more biological and nuanced way.
That's a great point. The brain is, after all, the ultimate example of a scalable and intelligent system. If we can understand how it works, we can potentially unlock new insights for building more intelligent machines.
Yes, but let's not forget that the brain is also a very complex and messy system. We shouldn't blindly copy its architecture, but rather try to extract the underlying principles that make it so effective.
And we need to remember that the brain operates in a physical world, constantly interacting with its environment. Any truly intelligent system must also be able to do the same.
Absolutely. Well, this has been a fascinating discussion. It's clear that energy-based transformers hold a lot of promise, but there are still many challenges to overcome before we can truly claim to have built thinking machines. We need more research, more collaboration, and perhaps most importantly, more critical thinking.
Agreed. It's an exciting field, and I'm looking forward to seeing what the future holds.
Me too. But let's keep our feet on the ground and avoid the hype.
Indeed. The journey towards AGI is a marathon, not a sprint.
Thanks for joining us on Cognitive Spirals. Until next time, keep exploring, keep questioning, and keep pushing the boundaries of our understanding.